C. Calculating the magnetic force on a strict current carrying wire. From the above experiments, we have plotted graph of F versus I, F versus L, and F versus B. We find that the induced force is directly proportional to I, to B, and to L. So we may write F equals K times BIL. However, the unit of magnetic field is chosen such that 1 Newton equals 1A times 1T times 1 meter. In other words, 1T equals 1 Newton per ampere per meter. And therefore, when the current 1A flows inside a magnetic field of 1T, 1 Tesla, the induced force per meter is 1 Newton. If the magnetic field and the current are not perpendicular, the component of magnetic field should be considered, which is B sine theta, where theta is the angle between the magnetic field and the current. Example 9. Calculation of the magnetic force. The famous left-hand rule helps you to find the induced magnetic force direction, which points into the paper in both cases. You may draw crosses to represent the forces which point into the paper. For magnitude, apply F equals IBL. For the case on the right, apply F equals IBL sine theta, where theta is the angle between the current and the magnetic field, theta. Example 10. Conductor rolling downhill. In this case, a current-carrying rod rolls downhill as shown. The magnetic field is vertically downward. It is not difficult to find the direction of the induced magnetic force. You are asked to find the resultant acceleration of the rod, and it must be downhill. So it must be FB cosine theta over M plus G sine theta. Some of you may still wonder about the free body diagram. Note that the normal reaction is not mg cosine theta in this case, as the rod can only move along the incline, and so its net force must be along this direction, parallel to the incline. So just consider the forces parallel to the incline is good enough. All other forces will be balanced by the reaction force R. Example 11. Measuring magnetic field. In this example, a digital balance is used to measure the magnetic force on a pair of magnets. Note that the orange wire is fixed in position, and so only the magnets may move, which will then. Note that the orange wire is fixed in position, and so only the magnets may move, which will then changes the reading of the balance. The balance reading starts from 145 grams, which is the mass of the magnets. The balance reading increases due to the downward magnetic force on the magnet. So we may tell that the magnetic force on XY is upward. Since the current flows from X to Y, we may find the direction of the magnetic field using left-hand rule, which directs from P to Q. Try it yourself. For part B. The graph of the balance reading against current is a straight line. We should first express the balance reading in terms of the magnetic force, and hence I. As I said before, 1 gram change in balance reading does not exactly correspond to 0.01 Newton. So there is minor changes of these values, but it doesn't affect the principle of the experiment. Now spend a couple of minutes to go through these examples and make sure you understand every single step here. Do Chap.6 on the next page.